Hey, good morning, everybody. This is Mr. Ainsworth at Great Oak High School here in Temecula, California, and we're in AP Pre-Calc here in 2025, and we're going to get started in our first lesson of the year. All right, and we're going to be talking about rates of change in a specific context, and so this one's called "Can we predict maximum heart rate?" All right, so let's read here. So understanding heart rate can be an important tool for an important exercise training, all right, and for monitoring cardiovascular health. One measure that is often calculated is your maximum heart rate right here, or HR max, okay? Maximum heart rate. Your maximum heart rate depends on your age, okay? So let's take a look at some data in a context and apply the concept of rate of change to this situation here. So let's take a look. Table below obviously gives our relationship between age and maximum heart rate. Just take a look at it here. 14-year-old has a maximum heart rate of 206 beats per minute. All right, BPM is beats per minute. And then as you get older, you can tell that the maximum heart rate goes down, and it happens to be a linear function. So maximum heart rate depends, okay, depends on age. So part one here says describe the relationship between age and maximum heart rate. All right, and as I just said here, if you take a look at the data here, all right, as you get older, all right, your maximum heart rate decreases by a certain amount, and guess what? We can figure that out. So let's write down what we see in the table here. So, all right, as a person, all right, gets older, all right, the maximum heart rate decreases. The maximum heart rate, HR, you could say, HR max, maximum heart rate decreases over time or as you get older. All right, just that's straight from the table right here. Like by how much? I don't know. We're going to figure it out by looking in the table here. It says predict the maximum heart rate of a 35-year-old and explain your method. Well, the 35 is not, okay, is not in the table, right? It's between obviously 25 and 40. But what we want to do is we want to figure out, how much is it decreasing per year? How many beats per minute is it decreasing? To do that, okay, we want to figure out the average rate of change and figure what's going on. So the age here, let's just call it the x values here. This is your domain or your input, okay? Domain is the input of the function. If we're going to write a function, which we're going to do in a little bit here. And the range here, the set of y values, we call it range, set of y values. And so what we want to do is figure out delta y and delta x, the change in the heart rate according to the change in age. So we need to analyze the table a little bit. So let's go ahead and do that. All right, let's take a look at the rate of change in the age. So from 14 to 18 is obviously a change of 4. All right, that we'll refer to as delta x here, or the change in age. Right? And then let's just go all the way through the table here and let's see if it's constant. And it's not. From 18 to 25 is a change of 7 or an increase of 7, so plus 7. 25 to 40 is plus 15. And then 40 to 50 is plus 10. So the rate of change in x is not constant. So just keep that in mind. From 50 to 72 is obviously a change of 22, so plus 22. All right, from 50 to 72. But what's going on in the maximum heart rate in beats per minute? Okay, and hopefully, if you can't do this in your head, then you can use a calculator, whatever you need to do. So from 206 to 202, there's a decrease of 4, so it's minus 4. We refer to this as delta y, or a change in y, or a change in the maximum heart rate. From 202 to 195, again, we're decreasing here, so the rate of change has got to be negative, but by how much? And that's a minus 7. All right, so from here to here is a minus 7. From 195 to 180 is a decrease of 15. From 180 to 170 is a decrease of 10. So you have to put the minus sign there, so keep track. Okay, if it's increasing, it's a positive number, the rate of change, and if it's decreasing, the rate of change is negative. So make sure you put the sign. Just don't write down 4, 7, 15, and 10. It's a minus 4. Okay, the maximum heart rate is decreasing as you get older, and from 170 to 148. That's a decrease of 22. Okay, 22. But what's the rate of change or the average rate of change or in beats per minute per year? It'd be kind of nice to know that because if we knew that, we can figure out what the maximum heart rate would be right here. Going back to the problem, maximum heart rate, or HR max, HR max, all right, for a 35-year-old, because we have data for 25 and 35-year-old. Well, it's 10 years later, but if we knew what it would be per year, it'd be kind of nice. All right, so take a look at this first one here. We know from previous classes, all right, the average rate of change is equal to delta y divided by delta x. In this case, it's change in the heart rate, all right, over time in age. So change in age, change in heart rate divided by change in age. So let's zoom in on the table here. So uh, change, so delta heart rate here, heart rate over change in age. That's basically what I want to do. And obviously -4 divided by 4 is -1. So this is a change, all right, in one, or a decrease of 1 beat per minute per year. All right, -1/1 is -1, or a decrease of 1 beat per minute per year. So let's see. So these are beats per minute. So BPM. All right, beats per minute. All right, per year. All right, -1/1. All right, it's the same as -1. Is that the same? Is it constant through the table? Well, let's take a look. From 202 to 195, or from 18 years to 25 years, there's a decrease of 7. Right, negative. It's a -7 over 7 years. So this right here has the same AROC, so the same average rate of change. So -7 over 7. Well, guess what? That's still -1. And then same thing here. The average rate of change is constant through the table. So this function must be linear. All right, -15 over 15. Well, guess what? That's still -1. And so this is a decrease of 1 beat per minute per year. That's how you interpret it. So it's a decrease of 1 beat per minute, all right, per year. All right, and that's how you interpret it. And by the way, interpreting your data is huge in this class, as you guys are going to find out. All right, so for linear, so this function must be linear because the average rate of change is constant. Let's write that down. So the average rate of change is constant. All right, and because of that, guess what? It's a linear function. We talked about that in our review lesson when we first started in the beginning of the year, in the first few days. So it's a linear function because for all linear functions, the rate of change is constant. It's a line, guys. It's not curved, okay? And notice that's why they gave you a linear function in the graph. So let's get back to the question here. It says predict the maximum heart rate for a 35-year-old. Well, if we know that there's a decrease of 1 beat per minute per year, right, from 25, right? Oops, let's not do that in red. Okay, so from 25 to 35 is 10 years, right? So it's a 10-year span, 10 years. It's a 10-year span. All right, so what happens here is there must be a decrease of 10 beats per minute per year, right? Or I mean, excuse me, overall. So if it's a decrease of 1 beat per minute per year over 10 years, right? So -1 is equivalent, all right, is equivalent to -10 over 10. So this is beats per minute. Sorry, wait, come on. Why is it my one number spelling? So beats per minute here, okay, over years. So there's a decrease of 10 beats per minute over 10 years, which means we have to subtract 10 here from our value at 25. So if a 25-year-old has a maximum heart rate of 195, so that tells me that we're going to take 195, I'm going to subtract 10 beats per minute. And so the maximum heart rate here, heart rate max, HR heart rate, the maximum heart rate for a 35-year-old must be 185 beats per minute, because it has to be 10 years, or 10 beats per minute less uh, than what we had at 25 years old, because this is a 10-year span. So for every year, there's a decrease of 1 per minute, so it has to have a maximum heart rate of 185. All right, number 2, the graph also shows the relationship. Okay, so we have a linear function in the table, and we also have the graph of the function. Okay, so notice the titles up here. So on the vertical axis, we have HR max, maximum heart rate. Okay, so HR max. And then on the horizontal axis here, we have the age here. And so what they did was they plotted the points for us and just drew a graph of the function. It says, what is the maximum heart rate of a 60-year-old? Well, we go on the horizontal axis here and we take a look at, we find 60 here, obviously, and we want to interpret what would that maximum heart rate be for that. So what we're going to do is we're going to go up to the function here. It's something you learned in Algebra 1. Just basically interpreting the graph here, and then we take a look at the maximum heart rate for that 60-year individual, and it happens to be 160 beats per minute. Okay, so nothing fancy there. So 160 beats per minute. And then it says, what age would you predict for someone who has a maximum heart rate of 200? Well, here you do the reverse procedure. So you find 200 beats per minute. So let's do that. So it's up here on the y-axis. You go to the function. Wherever it hits the function, you go down. And then you read the graph. And guess what? That refers to a 20-year-old. So a 20-year-old would have a 200 beat per minute maximum heart rate. So 20 years old. Okay, part C here, writing an equation that is used to determine the maximum heart rate of the individual who is X years old. Okay, so we're using X for the age here. We're using Y for the Y-axis here for the maximum heart rate. So we're using just typical variables here. And this is a linear function. And because it's linear, we need to recall what a linear function looks like. And from Algebra 1, right, all linear functions have a special form. And you guessed it, is y equals mx plus b, where m stands for your slope. All right, b represents your y-intercept. So just going over some basics right here. So what we want to do is we know the slope, which is your average rate of change, is -1. We already figured that in the table, okay, from above. So that's good. And then we just need to figure out the y-intercept. And if you look at the graph here, and if you zoom in here, it kind of looks like the y-intercept, or it intersects at 220 beats per minute. So there is your y-intercept. That's your b value. So b is 220. So writing a linear function, pretty straightforward in this case. All right, so here y is going to be equal to -1 beats per minute per year, right, times x plus 220. And this is the first basic way that you can write the function. You can use point slope form too. If you'd like, you can pick a point on the graph and use point slope form, or you can just use slope intercept form, make it easy. Now, in this class, we use function notation a lot. And so instead of y, we use f of x a lot. So f of x, f being in your function here, would be equal to -x plus 220. So using function notation. All right. Then in part D, it says, what do you think is reasonable values for x in your equation? Okay, now we're talking about x here, and x is in respect to the domain. So they're basically asking you, what is the domain of the function? Okay, so what are reasonable values for the domain? And then you just have to use a little bit of common sense here. Okay, now first of all, age cannot be negative. First of all, so it's not the set of all reals. So the minimum age would be 0, and then the maximum age would be, around 100, 105, because most people don't live past 100. If you see somebody in the high 90s, that's pretty extraordinary. But nowadays, we have people that actually reach the age of 100. So you can say the minimum 0, obviously, all right, all the way up to maybe 100 or 105. I'm going to write down 105 max. And this refers to the domain here. And so age, again, age can't be negative. We're talking about age here, not the maximum heart rate. So it's got to be something greater than or equal to 0 and all the way up to maybe 105. So the domain here, if you want to write an interval notation, is closed interval from 0 to 105. You could write it that way. Or you can say, excuse me, 0 less than or equal to x here, less than or equal to 105. Again, this is the minimum, and this would be the max. And then it'd be a reasonable, it says reasonable domain. So, and then it says, do you think it is possible, this is part E now, to have a maximum heart rate of 100 beats per minute? What would that be? So take a look at the graph here. So this is a y value. So you want to figure out, what would the age be for a maximum heart rate of 100? So go to the graph. Let's do that. Find 100. This is the y value now. And then if you notice here, using the graph is kind of hard because we don't have that extended all the way through here. So what would that be? What would the age be for a maximum heart rate of 100? Would that be even possible? Okay, and it would be definitely, this person would be definitely really old because the graph stops at 80, but exactly what would it be? And because we can't determine from the graph, what we're going to have to do is use the equation, all right? So use the equation here. So let's bring the equation here and use this right here. So if a y value is 100, all right, beats per minute, what would x be? I don't know. So, well, I mean, we're going to find it. So let's take the equation here and let's bring it in. So we know y is equal to negative x, negative 1x plus 220. That's the equation that we developed. All right, now if y is 100, what would x be? So 100 is equal to negative x plus 220. Okay, and then, solve for x right here. You can subtract 220. So 100 minus 220 is a negative 120. And if that's equal to negative x, just multiply both sides by a negative, and you get x is equal to 120 years old. Okay, and it says, do you think it is possible? Probably not. Okay, most people don't live past 105, and I don't know if anybody in history has ever lasted or has ever lived to 120. So really, this is not possible. Not possible because most people do not live, much past 100. Right, just using a little common sense here. Common sense. Okay, so we're just, believe it or not, we've only used Algebra 1 basics here. So, okay, and then right here, write a formula found above. Okay, while the formula found above is easy to use, research has found it to be less accurate for women. All right, the proposed function h of x here, which is equal to 206 minus 0.88x, to estimate the maximum heart rate, all right, for women that is x years old. All right, so x is age right here, and then h is your heart rate function, maximum heart rate function. And they ask you to evaluate the function and find h of 32, and then interpret your answer. All right, and explain it in the context of the problem. So underlearn, interpret, because this right here is an important part of the course. You not only have to calculate it, but you have to tell me what it means. Okay, so let's evaluate it first. All right, so h of 32. We have to substitute in 32, so 206 minus 0.88 times 32. And in this class, we're going to be using Desmos quite often. All right, so go ahead and bring in Desmos here and evaluate the function. So just type in 206 minus 0.88 times 32, and then round it to 3 decimal places if needed. And notice it's about 177.84 beats per minute. So 177.84 beats per minute. All right, so then it says interpret. So the interpretation of this would be for a 32-year-old woman. Okay, here's the interpretation, this part. Okay, a 32-year-old woman, this is the context of the problem, all right, would have, okay, a max heart rate of about 177.84 beats per minute. That's the interpretation. So you evaluate first and then explain afterwards. And remember, whenever they do this, even this is for the even on the AP exam, on the FRQ, you have to interpret and explain your results. Okay, and that is the basic essence of the lesson here. And so let's continue here. Let's go do a couple learning targets here. All right, so first thing that we learned coming in from the table here, up at the very top, is that we talked about the average rate of change. Okay, so the very first thing here that we have to understand that is if we, the average rate of change, so learning target LT, learning target number 1 here is the average rate of change in general is delta y divided by delta x in general, okay? And if it's linear, okay, the average rate of change is constant. So if it's a linear function, which as we talked about here and reviewed, y is equal to mx plus b right here, if linear, the average rate of change right here, AROC here, is constant. It doesn't change. So it's constant, okay, really important here, on any interval. Okay, and we also talked about the domain and the range. So the second basic learning target here, learning target number 2, LT is learning target, all right, is that the domain of the function here, domain, which typically is, we refer to it as x here, is a set of input values and the range, all right, typically referred to as y, but not always, all right, is a set of output values. All right, those are the two main concepts in the lesson so far. And then after each lesson here, after we explain basically the learning targets here, we go into the check for understanding and we apply it. And sometimes we do this individually and sometimes we do it as groups. All right. But I'm going to stop the video here, just it's the first one here. And then if you get stuck here, make sure you come to class here, work with me. And if you really get stuck, come in at the intervention or before after school, and I'll help you out. All right, that's the basic idea of our first lesson here in pre-calc. This is Mr. Ainsworth. Hopefully that helped you out. You guys take care, and I'll see you in class.